In this lesson, I'm going to show a few examples of building quadratic models. And we are doing this so that we can optimize a certain situation given whatever data we are giving. So we will be talking about maximum or minimum values in these certain models. So first, you have what law of demand is, and when that equation relates P and X, that's called the demand equation. And when that demand equation is linear, then our revenue model will be quadratic. So that's what this first example deals with. We have the marketing department at Texas Instruments has found that when certain calculators are sold at a price of P dollars per unit, the number X of calculators sold is given by that demand equation, X equals 21,000 minus 150P. So part A here, we're asked to find a model that expresses the revenue R as a function of the price P. Well, the revenue of something is equal to how many we sell times the price that we sell them at. So we're selling X calculators at price P. Well, we have our demand equation, X is the 21,000 minus 150P. So we can substitute that in. So R of P equals the 21,000 minus 150P times P, which is 21,000P minus 150P squared. You can leave it like that, or we're going to end up using the standard form of quadratic. So we can also write that as negative 150P squared plus 21,000P. Looking at part B, what is the domain of R? Assume revenue is non-negative. Well, we know that the 21,000 minus 150P has to be greater than or equal to 0. And then the P has to be greater than or equal to 0. If we solve that, then we get P has to be, let's see, if we subtract the 21,000, that's negative 150P, greater than or equal to negative 21,000. Divide by negative 150, you flip your inequality sign. So P has to be less than or equal to 140. And then same thing, we also know that X has to be greater than or equal to 0. The number of units we sell, we're not going to sell a negative amount of units. So that's also greater than or equal to 0. So our domain here is going to be between 0 and 140. All right, what unit price should be used to maximize the revenue? So here, we're trying to find the maximum. And if we look at our quadratic equation, our A term is negative 150. So we know that this parabola is going to be concave down. So we're going to have a maximum up here. And that maximum occurs at the vertex. And we can find that first by finding our axis of symmetry. So our axis of symmetry would be X equals negative B over 2A. Well, our X is just P. We're talking about P here. So I'll go ahead and change that to P. So that is going to be negative 21,000 all over 2 times negative 150. And that is equal to 70. So the revenue is a maximum when P is $70. All right, so we will make the most money when our price is $70. If that price is charged, what is the maximum revenue? So now we're trying to find our Y value of our maximum there. So we're just going to find R of the 70. And so we're just plugging 70 into our function. So that is negative 150 70 squared plus 21,000 times 70. And when you do that, you get $735,000. All right, so when we charge $70 per calculator, our maximum revenue is $735,000, but that obviously depends on how many units are sold. So in order to make that amount of money, selling it each at $70, $7 each calculator, we need to figure out how many calculators do we need to sell. So how many units are sold at this price? We're going to use our x equals 21,000 minus 150p. So x equals 21,000 minus 150 times the $70 price. And when we do that, we get 10,500 calculators would need to be sold at that price to meet our maximum revenue of $735,000. Next here, we're just asked to graph R. I've already got that here for us to look at. I just typed in the negative 150p squared, but instead of p, I used x. So we're doing it on the calculator. Plus 21,000p. I changed my window so that I could see the graph. So I made my x min 0, my x max 150 because my domain went up to 140. So I just went a little bit above. It just went by tens for my x scale. My y min I made 0. My y max, I went up to 740,000. We know that our max was actually 735,000, but I wanted to be sure I could see the whole graph and just made my y scale at 5,000. Okay, so that can vary just as long as you can see the whole graph on your screen, then you are just fine. All right, part G says, what price should Texas Instruments charge to collect at least $675,000 in revenue? Okay, we could do this by hand if we wanted. So to do that, we would just replace our P with $675,000. We could subtract and solve the quadratic. It's going to be easier to graph this. So I suggest graph y equals 675,000 along with the graph we already have. And then just to show you what that would look like, there's going to be a line that goes straight across your graph like that. And we are just going to find their two intersection points. So really, if you want to collect at least $675,000, that's going to happen from this first intersection to the second intersection. At all of those points, you're making $675,000 or more. So if you want to use your graphing calculator to do that, you're just going to hit second trace and then go to intersect. And it's going to ask you first curve, second curve, guess, I believe. And it's just saying first curve is the parabola, second curve is your line, guess. Just go to the intersection point and you're going to hit enter 3 times. And when you do that for the one on the left, you get the x value to be 50. And when you do that to the one on the right, you get the x value to be 90. So what price should Texas Instruments charge to collect at least $675,000 in revenue? I'm just going to put they should charge between $50 and $90. Okay, so they could charge exactly 50 and they would get exactly 675 as long as they sold that many. And then same thing, they could charge exactly 90 and still reach that $675,000 in revenue. All right, next here we have a farmer has 2,000 yards of fence to enclose a rectangular field. What are the dimensions of the rectangle that enclose the most area? So he has 2,000 yards of fence. That's going to cover the perimeter around the outside. We know to find the perimeter of a rectangle, we add up all the sides. So x plus x would be 2x. W plus w would be 2w. We know that he has 2,000 yards. So we can plug that in. We know we're trying to enclose the most area. Area is length times width, which in our case is x times w. So we want to write the area in terms of either x or w. So that means we need to take this equation up here and solve for either x or w. It doesn't matter unless it's specified and tells you which one. Like your homework might ask you for, write the function of the area with respect to the x value or the w value. It doesn't really matter. We're just going to go ahead and solve for w. So if we solve this for w, 2,000 minus 2x equals 2w. Divide everything by 2, and we get w equals 1,000 minus x. Well, now we can plug that in. So the area with respect as a function of x is x times 1,000 minus x. That's 1,000x minus x squared. All right, so at this point, we are going to find the max of that area. You could graph and use the maximum feature in your calculator. It's probably the one with us work here, but we can also just do our x equals opposite of b over 2a. The opposite of b would be negative 1,000 over 2 times a would be negative 1. That's negative 1,000 over negative 500, which is 500. So, think about this. If x is 500, those add up to 1,000, so we got 1,000 more yards of fence to work with, but we got 2 sides of the fence left, so these both also have to be 500. All right, so the largest rectangle that can be enclosed by 2,000 yards of fence, the dimensions would be 500 by 500. Width equals 500 yards, and length equals 500 yards. Multiply those two together, you get 250,000 square yards, so the total area enclosed to maximize would be 250,000 square yards. Notice, to maximize that rectangle, it's actually a square to maximize it. 500 by 500 would be a square. And last one here, we have the Golden Gate Bridge, which is a suspension bridge, spans the entrance to San Francisco Bay. It is 746, has towers that are 746 feet tall, and those towers are 4,200 feet apart. The bridge is suspended from 2 huge cables more than 3 feet in diameter to 90-foot wide roadway, and it is 200 feet above the water. The cables are parabolic in shape and touch the road surface at the center of the bridge. We are asked to find the height of the cable above the road at a distance of 1,000 feet from the center. So here we have a picture. We know it's parabolic in shape, so we're going to use y equals ax squared. That's our basic parabola there. Well, we know some y and x values. There's multiple ones on here. I'm going to choose to use the positive ones. So we're going to plug those in and get 526 equals a times 2100 quantity squared. Solving for a, we're going to divide both sides by 2100 squared. That's a really large number, so we're just going to leave a as 526 over 2100 squared. So our model is y equals 526 over 2100 squared x squared. So use that as our model. And the question is, find the height of the cable above the road at a distance of 1,000 feet from the center. Well, 1,000 feet from the center, that's our x value. We're trying to figure out that y value there. So we are going to take the 1,000 and plug it in for x. So y equals 526 over 2100 squared times 1,000 squared. And when you get that, you get y is about 119.27 feet. All right, so the cable is about 119.27 feet above the road at a distance of 1,000 feet from the center there of the bridge.